Okay, this is SpongeBob challenge number 29. And what we'll do is find the domain. Last time we found the domain by looking at the graph. We didn't care about what equation made the graph. We just looked at the graph that was made by an equation. And from that graph, we were able to determine what the domain and range was. Okay. Now we're going to find the domain by looking at the equation. And the first type of equation I want to look at are equations that are polynomials. In general, polynomials have this look. Um, Number in front of x to a power plus a number x to another power, smaller power, all the way down to a constant. I guess that can't be seen off screen. Let me bring that over a little bit. So polynomials again are um, some x to a power that's a natural number, okay, like 1, 2, 3, 4, 5, 0, or whole number 0, 1, 2, 3, 4, 5, plus a number of times an x term that has a smaller power, all the way down to x to the first powers, and then finally down to a constant. Anything that has that type of progression, this is a polynomial. So when we have polynomials and we graph them, we notice that their domains, it's always all real numbers. The x values go to the left and to the right forever. So we're going to start off saying that since this is a polynomial, a very small one here, the domain for this will be all real numbers. The graph of that looks like this. And furthermore, the interval notation is negative infinity to positive infinity. And let's see. Oh, we'll leave it at that. Well, we can also say x is all reals. Okay. So for anything that looks like this, that's a polynomial, you will say that a domain is all reals. Okay, let's get rid of this. Okay, now what happens when we have a polynomial over a polynomial, which is called a rational function, okay, when polynomials are in fractional form. Okay, to find the domain of these, the process is this. You look at the denominator, which is here, negative 4x, and we set that not equal to 0, and then we solve for x. This little process right here, taking the denominator out, setting it not equal to 0, will give us our domain. So let's solve for x, we'll divide by negative 4 on both sides. And we end up getting x is not equal to, and 0 divided by negative 4 is 0. So this is our set notation. That graph looks like this. The 0, the hole in it, and you have both sides that equal the number line here. So your domain can be written this way, or negative infinity to 0 parentheses, which is this side right here, union with the right side, which will be written as 0 to positive infinity parentheses. So this gives you all three forms: set notation, the graph, and interval notation as a domain. Okay. All right, number 3. Number 3 is also a rational function, so we will take the denominator out, x plus 5, set it not equal to 0, and that will allow us to find our domain. So we'll solve for x by subtracting 5 from both sides. And we end up with x cannot equal negative 5. Okay, so that's the domain. Another way to express the domain is as a number line. We put an open circle on negative 5 and put the number line on both sides. So that's the number line for the domain. All numbers except for negative 5. And then the interval notation for this would be negative infinity to negative 5, parentheses, union with negative 5 to positive infinity. This represents the left side right here, and this over here represents the right side. So this is your domain. Okay. Number 4, once again, we're looking at a rational function. And notice that we're kind of ignoring the numerators. There will be a time when we get to higher mass that we'll kind of look at the numerators to see how they affect the domain. But for now, we're going to focus on the denominators. And to find the domain, we take the 4x plus 2, we set that not equal to 0, and we're going to solve for x. So we'll subtract 2 from both sides. I'll get 4x is not equal to -2. Then we'll divide both sides by 4. And we'll get 1x is not equal, and we'll divide this by 2, divide this by 2, and we'll get -1/2. Okay, and that's your domain. All real numbers except for -1/2. Okay, the number line for that is this -1/2 here. And the inner notation is negative infinity to -1/2 parentheses, union with the right side, which is 1/2 to positive infinity. This represents our domain. Okay. Now, as I get into demonstrate number 5, 6, and 7, I want to kind of go over a little bit what a domain was. A domain was a way of demonstrating all possible numbers that can be put into an equation. I also say all possible input. What numbers can you use to put into an equation? You look at your domain to see what numbers can be used. And I can say I can use any number except for -5 on this one, and any number except for -1/2. And as we saw with the polynomials would allow any real number as a domain value. You can use negative numbers, 0, positive numbers, everything, all numbers work inside polynomials. The only trouble you're going to start having when you start having these rational functions, we have to do a little more work. Okay, let's take a look at number 5. So we're going to take the denominator, 4x² minus 9, and set it not equal to 0. And then we're going to solve for x. So this is the difference of two squares. So we'll take the square root of 4x² and the square root of 9. This is going to give me 2x and 3. Okay. There, this factors into two polynomials. Sorry, two binomials. First one is 2x plus 3. The other one will be 2x minus 3. Then we want to solve for both of these. So we have 2x plus 3 set not equal to 0, and 2x minus 3 set not equal to 0. And I'm going to solve for x on both of these. So subtract 3 from both sides. Gives me 2x and -3. And then dividing both sides by 2 gives me x not equal to -3 over 2. Over here, I'll add 3 to both sides. I'll get 2x not equal to 3. And divide both sides by 2. So that x cannot equal 3 over 2. All right. What's the number line look like for this? Well, this number line actually has 2 gaps in it. There's a gap here at -3/2 and another gap here at 3/2. So those two values can be used. Also, to represent this side right here, this will be negative infinity, bad infinity, to -3/2, union with this part right here, which is everything from -3/2 to +3/2, and this part right here, which is everything from 3/2 to +infinity. Again, not including the -3/2 and 3/2. So this is your domain. Or 3 expressions of the domain. Okay, let's look at number 6. Number 6, we're going to take the denominator out, x² minus 9x plus 18. and set that not equal to 0. And we're going to solve for x by factoring. Factor this into two binomials. And for the x squared, that'll be the first term. We'll make that into x times x for the first term. The last term will be made out of 18. Now, 18, there are lots of choices for that. There's 1 times 18, there's 2 times 9, and there's 3 times 6. Okay, I'm going to start with 2 times 9 to see if that works. So here we go, 2 and 9. In the middle, this will give me 2x. Put these together. And on the outside, these two will give me 9x. This indicates that the signs have to be the same here. So they either have to be plus, plus, or minus, minus. And we have to end up with a negative 9x. So if I use a minus, minus, this becomes a negative 11x. And it doesn't match, so this doesn't work. Okay. So let's try this again. Two binomials. And first we'll have x times x to be x squared. So the 2 times 9 did not work. I'm going to try the 3 times 6. So 3 times 6. In the middle or inside, this gives me 3x. On the outside, this gives me 6x. Here we need same signs, and we have to get a negative 9x. So the same signs we're going to use is a negative and a negative. And these two do become negative 9x. So this is the proper way, negative, negative. So negative here, negative there. Now let's solve for x. So if x minus 3, set that against 0. And with x minus 6, set that against 0. And we're going to solve for x. Add 3 to both sides, and I have x cannot equal 3. And add 6 to both sides here. And we have x cannot equal 6. So those are two numbers that we cannot have in the domain. So let's write a number line that excludes these two numbers. And the number line will look like this. It'll have two gaps right here at 3 and 6. Now, the interval notation for this will be negative infinity to 3, union with the middle part, which is from 3 to 6, then union with the last part right here, which is 6 to positive infinity. All right, give me just a second. Gotta open up the door, and then we'll do number 7. Okay, number 7. Let's take a look at that one. Number 7, we have x over 2x squared plus 7x minus 15. Okay, so getting the domain, we'll take the denominator out. 2x squared plus 7x minus 15, and set that against 0. Okay, so it can't equal 0. And we're going to try to factor this into two binomials. And for the first term, it has to become 2x squared, so I'm going to say 2x times 1x. That'll give us 2x. Now the 15 is a little tougher, because that could be 1 times 15, or 3 times 5. Okay. Or it could be 5 times 3. A lot of choices there. Okay, I'm going to try, let's say, 3 times 5 first and see what happens. So 3 times 5. And in the middle, this will give us 3x. And on the outside, this will give us 10x. Okay. Our signs have to be different. And we need to get a 7x. So can I use different signs on these two and get a 7x? I think so. If I use a negative here and a positive there, this will combine to become a 7x. So I got it the first time. So negative first and then positive. Negative first and then positive. So let's write this as 2x minus 3, set that against 0. And we have x plus 5, set that against 0. And we're going to solve for x on both sides. So adding 3 to both sides, we'll get 2x and cannot equal 3. Okay, we'll divide by 2 on both sides. And we get x cannot equal 3 halves. Okay, over here, if I subtract 5 on both sides, we immediately get x cannot equal -5, and that's solved. Now, let's put these two on the number line. Now, on the number line, -5 will be on the left side, whereas 3 halves will be on the right side. And that's how the graph would look if you're looking at the domain as a number line. You'll see these two gaps where these two numbers cannot be used. Furthermore, interval notation, we will have this portion right here will be represented by -infinity to -5, parentheses, union with this part right here, which is from all the numbers between -5 and 3 halves. And then this portion right here, union with that, this will be all the numbers after 3 halves. And that'll be your domain, or your 3 demonstrations. I'm sorry. Let's do that a little better. Okay, these are your 3 demonstrations of the domain.